3, 2, 1.
Can I say something?
Greetings and welcome, friends. Today we are solving exponential equations using logarithms. I am not kidding at all. This is going to be amazing. Now, you might recall that we've been able to solve exponential equations when I could rewrite both of them in terms of the same base, right? But what happens if I want to solve something like 2 to the x equals 3, right? And we're like, oh man, I don't know what power to raise 2 to that would give me 3. Now behold this. Now we know that if I have a log equal to a log and they're both of the same base, I can drop the logs from both sides. It turns out similarly, we can reversify that concept and add a log to both sides. So let's log both sides of this equal sign here. So log it. And technically, I could pick any base that I want. I'm going to do log base 10 because that's typically what our calculator speaks in. So this is the same as, I guess I don't need an equal sign there. Log base 10 of 2 to the x equals log of 3, right? So I just added a log to both sides. And now how is that going to help me deal with this x? What property of logarithms gives me access to that x? What can I do?
Oh, you bring it up front.
Put it up front. I like it, right? Yes. The power property of logarithms. Very powerful, right? We can pull that out front. So I'll have x times log 2 is equal to log 3. Now remember, log 2 is just some number. So what would I do to get x by itself? X is being multiplied by some number?
Square root?
Nope.
Oh, shucks.
Divide both sides by log 2. So I'm going to end up getting, right, these would cancel out, and I'll get x is equal to whatever log 3 divided by log 2 is. And I could just plug that in a calculator or check up a table or something like that. Log 3 divided by log 2, and I'm careful with my parentheses, I get 1.58450. And we've just now been able to solve that problem previously unsolvable to us. What? We can solve equations with variables in exponents now. What? This is crazy. And just to verify as a check, what this is saying is, and you don't have to write the check, that means 2 to the 1.5850 should equal 3-ish. And what is 2 to that power? 2 to the second ants. I get 3 equals 3. What do you know, friend? We just solved it. So, let's put this to use. Well, the check wasn't necessary. I was just verifying it for your sake. So, you guys might recall, maybe you've done some work with exponential growth. And here we are. Bam. So there's a formula for exponential growth. And I believe you've seen this before. Growth. Uh-oh. Lagging a little bit. Oh, there it goes. All right. And the formula for exponential growth is A equals P times 1 plus R over N to the NT. All right. And this is not for simple interest, but for compound interest, right? And I guess I'll define what some of these variables represent. A is the end amount. P is the initial amount. R is the rate as a decimal. Decimal. And N, this is the weird one, is the number of times compounded per time period, I guess, per T unit, per unit of time, I guess. I'll just call it t. And t is time. I'll throw that over here. T is time. All right. Typically, time is measured in years because this type of exponential growth for compound interest is usually used just for like banking, and you're usually interested in how much money you'd have at the end of each year. Compound interest. So.
Wait, is that like number of times?
I'll explain that more in the next example.
Is that time?
So if it compounds, say, daily, times, yeah, plural. I see what you're saying now. So if my interest compounds daily, then n would be 365, where t is the number of years. Right. So here we go. Let's do an example of this. Exemple. How long? This is a very pertinent question. Would
I
it
like that
take?
word. That's my favorite word.
Pertinent
Yes. Yeah. Essential.
to have $1 million
Wow.
in an account let's see if we invest, say, I don't know, say I put 10 grand in an account at let's say 8.25% interest. That would be a nice chunk of interest right there, and it compounds monthly. Monthly. There we go. So here's the question: how long would it take this account to reach $1 million? Okay, good question. So let's see if I can go through and define some of my variables here. What is my ending amount that I want? $1 million. You want $1 billion?
What's the word in the next step? Yeah.
If we, yeah. So let's see. We end with $1 million. We started with the initial amount, the principal, right, is 10 G's. Right. The rate would equal, as a decimal, 0.0825. Importante.
Very importante.
Question, what do you think n is going to be? Number of times compounded per year? 12. There are 12 months in a year. And what I mean by compounded is that your interest is being stacked on top of your interest. All right? So instead of just earning the same amount each year, like if I put $100 in at 5%, I get $5 at the end of the first year. But the next year, not only am I earning another $5, but I'm also earning 5% on my first year's $5. Very good point. Because you have to write the percent as a decimal for the rate. Otherwise, it will not work.
Why would it be 8.25?
Well, 8.25 would be like 825%. So I have to write it as 0.08 because 100% would have been like 1.00.
I don't get why n equals 12.
And it is 12 because there's 12 months in a year, compounded monthly. So if it was quarterly, n would equal 4. If it was weekly, n would equal 52, right? If it was secondly, it would be whatever number of seconds there are in a year. And eventually you'll actually, not this time, but eventually you'll see that there's also a compounded continuously. That what if we divided time infinitely many ways and had it compounded its interest for each one of those units? What would that look like? And that actually requires calculus to have derived, but the formula actually isn't that crazy.
Good thing I don't take calculus.
So let's write this equation. So I'm going to have 1 million equals 10,000 times 1 plus the r, 0.0825, divided by n, which is 12, all to the nt, right? So that's 12t. And notice if I could solve for t, that would tell me how long it would take to get $1 million, or $500,000, right? Because technically I already invested the 10,000. So in order to solve this, first thing I'd like to do, I'm going to divide both sides by this 10,000. Right? Why not? So let's see here. That's 1, 2, 3, 4. 1, 2, 3, 4. That's going to leave me 100 on this side, right? When that cancels out. Times, let's see, this is going to be 0.0825 divided by 12. 0.0825 divided by 12 is 0.006875, and plus that 1 would be 1.006875, all to the 12t. Now my problem is, now here's your problem. I don't know how to get the variable out of the exponent, do I? Or do we? What did we do up here? I took the log of both sides. What? Same idea here. I can simply take the log of both sides, and technically any log that I want, doesn't have to be base 10, but typically I'll just do base 10. So log of 100, actually we could even calculate what that is. 10 to what power is 100? What? Second power. Equals log of 1.006875 to the 12t. And what property of logarithms could I use that's going to help me out here? Power property. Sneezes. So I'll have 12t times the log of 1.006875. And to solve for t, well, remember 12 and log of this thing are just numbers, so I'll just divide both sides by 12 times the log of 1.006875. Are you guys getting sick of writing 1.0086 or 6875 yet?
Yeah.
1.006875. So I'm going to end up getting t equals 2 divided by that. So let's do that carefully. 2 divided by, let's see, 2 divided by, and I'm going to be careful plugging this in parentheses, 12 times the log 1.006875, and I'm double close parentheses there, and I get t is equal to, how long do you think it takes? 56.0119 years.
That's a lot.
56 years. Right? To go from 10 grand to $1 million at the 8.25% interest rate. Right? So, and actually there are some cultures, actually, when they invest, like specifically the Jews, there's a proverb that says that a righteous man leaves an inheritance to his grandchildren. So they've actually incorporated that principle in some groups of the Jews, where they'll actually invest money but not leave an inheritance to their first generation, or not necessarily a large inheritance, and then leave it to the second generation, because time is the most powerful variable in this equation, and that results in 2 lifetimes for it to really exponentially grow, which ends up having a much greater legacy on their family.
I wish my grandparents were Jewish.
Interesting. So let's look at a fancier math problem now that we've done some compound interest.
Imagine the first parents that did that. They're just like, hey, I'm going to give it to my grandchildren. Like the first, second generation was just screwed. Basically, just.
It's like, thanks, Mom and Dad. I would have loved to have some money from you guys. Here, how about a crazy problem like this? 8 to the 2x minus 5 equals 5 to the x plus 1. So Joey, you might remember that we had solved problems such as this when we could rewrite 8 and 5 as the same power. However, no tenemos, right? We don't have that ability in this case. I can log both sides, so let's log it. Log, log. And then, since we're already good at this, I'm also going to move these exponents out front, all in one step, because that's how awesome we are. Log sum. So let's see, this will be 2x plus, let's write a nicer looking x. 2x minus 5 is now all in front of log of 8 equals, and then x plus 1 is all in front of log of 5. Now one of the things I want to point out, notice I parenthesized this stuff, which means that the entire thing is going to be multiplied by log 5 or log 8 respectively. And the reason I had to do that was this entire thing was an exponent, so this entire thing has to be multiplied by log 5. All right, so don't forget those parentheses there. So, well, I still can't do much here, so I'm actually going to distribute these logs to their respective buddies. So I'll have 2x log 8 minus 5 log 8 equals x log 5 plus 1 times log 5 is just log 5. And then my next strategy is to bring the logs with x's to one side and the logs without variables to the other. So in order to do that, well, here's a log with an x, here's a log with an x. I want to bring this over here. How could I move that? I'll subtract x log 5 from both sides. And just remember that like log 5 is just some number, right? So this equation is really no different than if I had 2x minus 5 equals x plus 1, right? And I would just subtract the x from both sides to bring them together. Same idea, same principles are applying, so don't get scared off by the fact that there's logs around. And I want to move this to the other side, so I'm going to add 5 log 8 over here. So behold, I'll have over here 2x log 8 minus x log 5 equals, and over here the x log 5s are gone, so I'll have log 5 plus 5 log 8. Well, not entirely, no. So, now, here's the question. I've got an x in both of these terms. How could I write this as only a single x? Challenge.
I don't know, Mr. Roddy.
Well, check this out. Yoink, yoink. A yoink, a yoink. Aha! So watch, this is actually going to rewrite this whole side with just a single x, which is exactly what I want. So x times 2 log 8 minus log 5 equals all the same stuff, ditto marks, right? And now what would I do? Now 2 log 8 minus log 5, this is just some number being multiplied by x. How do I get x by itself? What would I do to both sides? Yeah, divide both sides by this big ugly thing, right? So x is going to equal approximately this whole thing divided by this whole thing, right? And I'm going to have to be very careful plugging these in. In fact, when I do so, I'll have to put parentheses around this and around this. So it's actually going to have moments of double closed parentheses, just so you are aware. So let's see, I've got log 5, close that parentheses, plus 5 log 8, close that parentheses. Oh, I need a parentheses around the whole numerator, so I'm going back, second insert. Let me show this to you on the calculator if I can. So my numerator, it's got the blurries. Come on, focus here, focus. Zoom in, maybe? So notice I had to put parentheses around this numerator. There it goes. So it's got open parentheses and double close parentheses. So this is just the numerator. And now I'm going to go over here and hit divide. And before I type in the denominator, I'm going to open a whole new set of parentheses. All right? And what I'm going to enter in here is this guy. So 2 times log of 8, close its parentheses, minus log of 5, close its parentheses, double close. And let me show you a glimpse of that again. So notice that the whole denominator, right after the divide, I had to put open parentheses and that whole thing, close parentheses, just to ensure that this calculates correctly. So let's hit enter, 4.7095.
Hey, I'm from Greek one average.
I like it. All right, so not crazy. It's weird looking at all these logs. I think it's interesting when math becomes more letters than numbers. But that's fine. They behave, right? Log of 8 is just a number, right? So some of the interesting steps were log both sides, pull the powers out front, distribute. Then I brought the logs with x's to one side and the logs without x's to the other. And then I GCF'd, well, technically I factored out an x, not necessarily the greatest common factor, and then divide both sides by what was left over, is how that ends up working. So let's see, one more thing I want to point out that we've technically been needing in some cases, but have yet to discover. We'll do discoveries in actually blue. How about discover? Discover. Here we are. Now, let's say I've got a to the p equals n. All right. Now, this is a exponential form. How would you write this in logarithmic form? You guys remember how to do that? I know it's been the weekend.
Base A
Log base a.
whatever equals P.
Log base a of n equals p. Yep. You had the right layout. Just verbally improve that. That's all. Not bad, though. Not bad. So that's what that's equal to. But let's see what happens if I apply my new take a log of both sides trick. Let's see what happens. And let's just say this is log base b. Some unknown base. Could be any base. Any base. So let's see. I'll have log base b of a to the p is equal to log base b of n. And using my power property now, I could yoink this out front. So p times log base b of a is equal to log base b of n. And this is equal to p over here. What if I wanted to solve for this here?
Divide by log base B of A.
Divide both sides by log base b of a.
You're going too fast.
Don't worry, I'll go back to this if we need to. So I'd end up getting that p is also equal to log base b of n divided by log base b of a. And therefore, if this is equal to p and p is equal to that, those two things must equal each other. And this is called the change of base property. Base. Here we go. So change of base property is the thing we just discovered. Change of base property. And what it says is log base, what was it I had? A of n is equal to log base b of n over log base b of a. Now why is this helpful? Because so far, well, in one of the cases it's helpful is, so far we've realized that our calculators only speak in log base 10. Technically there's also log base e, the natural logarithm. But what happens if I wanted to calculate like log base 2 of something? Well, this is how we would do it. So let me show you how to do this. And this is one last short, swift example. Let's say I want to calculate what is log base 2 of 3. I can't plug that into the calculator willy-nilly. But what this is saying is that this, all right, these b's could be any number I want. I could pick my base. Let's do log base 10. So this is going to be the same as log of 3 over log of 2. It also could equal ln of 3 over ln of 2. We haven't talked about what ln is, but that's the log base e. It also could equal log base pi of 3 over log base pi of 2. All right, any base I want, I could plug in here and get an approximation. So let's plug in log 3 close parentheses divided by log 2 close parentheses, and I get 1.58450. Which is the answer that I had way back at the beginning when I divided this earlier in the day, earlier in this lesson rather, right when I did divide that out. So I just want to point out that if I have a base that doesn't work, all right, can't plug this base in. Then we just use this change of base property and write it as whatever base we want. And that's the idea. So anyways, thanks for watching, Internet friends. Bye-bye.